So let's take the same equation, 3x squared plus 4. So y equals to 3x squared plus 4. What I'm guessing is that all of you have done differentiation before. Maybe you don't know you don't remember everything. Maybe when you learned, you didn't learn very well. That's perfectly fine. May have been a while since you've done differentiation and you've forgotten everything. That's fine. But I'm guessing that all of you at least know what differentiation or what calculus is. So if you remember the formula for differentiating something, which is, let me just write that down here on this side. So suppose you had y equal to x to the power n. N is 8. And you wanted to differentiate that. What you would do is that the power would come to the front, x n minus 1. This was the formula. So for example, if you have x equal to x cubed, and you differentiated that dy dx, you'd get 3x squared. And you may have wondered why. What is this that we're doing? How does it make sense? We're just memorizing a formula, but where is this formula coming from? So that's what I'm going to talk about right now. So what we have seen here is that if we apply the difference quotient, if we apply the different quotient to this equation, so limit change in x approaching 0, change in y divided by change in x, what we are going to get is so suppose we're moving from x0 to x1. So what we are going to get is 3 x0. Now let me simplify this for you guys. I may be making it a bit more confusing. Let's just go back to a and b the way we had done. We are moving from a to a plus b. That's just a simpler way of doing that. And once we did that, this is where we had arrived. So let me write that down. 6a plus 3b. What we had also realized is that if we are imposing the limit that change in x will approach 0, then what we saw is that b would become 0. As a result, what we end up with is just 6a, right? And what is a? A is just the value of x. So we can just write this at 6x. Remember, because a right here is just the initial value of x, where we are starting off with. Basically, x is equal to 3, right? 6x. And now notice that if you had differentiated this dy dx, you would have gotten 6x, which is what we have here. So what you need to notice is that we start off with the average change, and then average change gives us basically the average change in y over an interval or over a range of x. To calculate the instantaneous change, we impose this limit, and this is dy dx. Okay, that's it. We effectively, as we were deriving the difference quotient right here, I had shown you guys what differentiation is. You may not have known this before, but now you do. There are different ways of writing this. Sometimes you will write it at f prime x. So this, they're all the same thing. What they do these give you instantaneous change, nothing else. So here's the thing. Remembering the formula for differentiation is very easy. If you have something like y equals to 3x squared plus 5x plus 2. Okay? So all you need to know, this is just a revision, is convert this into this form. This is 3x squared plus this is 5x to the power 1 and this is 2x to the power 0, right? Because anything to the power 0 is 1, so it becomes 2 again. And now if you want to differentiate this, you just use this formula. So dy dx is going to give you, we have a 3 here, multiplied by this power x 2 minus 1 plus 5 multiplied by this power 1 x to the power 1 minus 1 plus 2 and then this power times 0 x to the power minus 1. So we multiply this 2, we get 6 x to the power 1, multiply this 2, we get 5x to the power 0, plus we multiply this, so we get 0x to the power minus 1. So if we simplify, what we are ended up with is 6x plus 5. That is differentiation, right? So the reason I showed you guys difference quotient is that if you apply the difference quotient, you will get the same answer. Okay. So if you do what we had done here, right here, we've taken a function, we've applied the limits, and we have ended up with this value right here. If you do the exact same thing to this equation, you will end up with this answer. Okay? So this is just to illustrate that what you know as dy dx is the same thing as the difference quotient. During this course, of course, this is probably the last time we're going to talk about difference quotient. We are going to stick to dy dx, the differentiation formula, because it's easier and quicker to do. But it is useful for you guys to know exactly how the formulas for differentiation is derived. As you go through chapter 7 and chapter 8, you will come across some complex differentiation formulas. Just keep in mind that the theory, the understanding behind all of them is exactly the same. All that we're trying to do is calculate the instantaneous change. We have different types of equations. Now, different equations will take on different forms. Some will be easy, like this here. This is quite easy. Some will be more complex equations. And so for different types of equations, we will be using different formulas. But at the end of the day, everything you do in differential calculus in Eco 201, that's everything you do in chapter 7 and 8. It all boils down to calculating the instantaneous change. Okay? So for the last time, let's do this again. We have a curve like this. And what we are interested is finding the difference between these 2 years, XA and XB. Now the problem is if we connect these 2 points, we ignore a lot of things. We ignore this point, we ignore this point, we ignore this point and this point, and we are just assuming that the increase has been like this. Or even worse, excuse me. Suppose this is what it looks like. As a policymaker, you're trying to change trying to predict what had happened during the year. This is the figure we get at the beginning of the year. This is the figure we get at the end of the year. And if you take the average change at the beginning of the year and end of the year, you're going to see that there has been no change. And suppose this is the diagram for food availability. And if you do this analysis, what you're going to think is that food availability during the year was fairly constant. People had the same amount of food they had in January, February, March, April, and so on. It was exactly the same. But that's not the case. The reality is that in some month, there was more food available. In some months, there was less available, more available, less available. So doing an average analysis is not good enough. So we hone down to something called an instantaneous change. So if we did an instantaneous change analysis at this point, what we would see is that availability of food is increasing. From day to day, how much food is available is going up. At this point, what we are going to see is that food availability is going down. How much food is available at this point as well, how much food people have is going down on a day-to-day basis. And then again, at this point, food availability is going up. At this point, it's going down. And you see, this offers us a much better way of analyzing the economy. And that's what differential calculus is in ECO 201. We're trying to calculate the instantaneous change. If there is a very small change in x, not a range, a big range like this, if there is a very small change in x, what is the change in y? Okay, that's it. Now that you guys understand this, hopefully you have solved a few problems from chapter 6. Now that you guys understand this, why don't you go on to chapter 7 and 8 from the book, and hopefully you will understand things a bit better. And if you don't, obviously you have the live sessions with your instructors, but hopefully this helps. Okay, so good luck.